Hello, very good morning to everybody. I'm Leona from Wizlogix, the host for today's WizConnect webinar. In the description of this webinar, we mentioned that RF has gained a reputation for being a black art. In fact, to work successfully in RF, an engineer only must remember some basic principles, understand the fundamentals of electronics, and be careful and rigorous in the practices. So this webinar will act as an introduction to RF and give a teaser for a course being offered online by Wizlogix together with Dr. Malcolm on the fundamentals for working in the RF world. We are honored to have Dr. Malcolm Smith, the director of AnalogueSmith, with us to speak about today's topic, get hold of the principles of radio frequency. Malcolm, please.
Okay, everybody. So today we're going to have a quick teaser on the basic introduction to RF. There will be a much longer course, whole week, 5 days, 1.5 hours a day, so 7.5 hours of course, just on an introduction to RF, going over various things. So today's is just a little sliver of what's available. Okay, so first I'd like to introduce our AnalogueSmith. So we're a design house. We specialize in analog and RF design for IoT sensor products in particular, but basically we cover all sorts of different areas. So we have IC design experts. There are associate fellows from Bell Labs and other US companies who work with us. And we have experts in SerDes and PLL and mixed signal and various analog and RF systems. So we also do board design, so RF mixed signal, analog type board design and antenna integration. And we're bringing up the skill set in embedded and firmware as well. So if you have any design needs, either big projects or if you need individual consultation, if I can't cover it, certainly one of our fellows can. And we're very pleased to make the introduction for that. So 3 questions. What is the impedance of the system I'm working in? Very important that you know that. Usually 50 ohms, but doesn't have to be. And in fact, as you move up and down in frequency or you move on and off chip, that impedance can change. So what frequency am I working at? Also very important. We'll come to that a bit later. And then where is the ground? Okay, it sounds obvious, but it's important that you know where your ground is. Okay, so why is impedance important? Classic, probably learnt it in your first year at university if you were studying for an EE degree. So maximum power transfer. So we have a voltage source and we have a resistance associated with that voltage source because it's not perfect, it's not a superconductor. And so what value should we make the resistor that the voltage source and its associated resistance is driving? So what should the value of RL be in order to maximize the power transfer between the voltage source and its resistance and that load resistance? Okay, so here what I've plotted is the actual power that's available versus the ratio of the load resistance to the generator resistance. And it's a log scale, so things are a bit funny, but basically, so this point here is a ratio of 1 to 1. Okay, so the load resistance is the same as the resistance in the generator. And if the load resistance is really low, you can see we could get a lot more power, but that power is actually being burnt off in the generator resistor. Okay, so if you look at actual power transfer, we get the maximum available transfer when the 2 resistors are at the same value. So when the load resistor is at the same value as the generator resistor, we get maximum power transfer, and it's 50% or half. Half the power goes to the load resistor and half the power goes to the generator resistor. Okay. What that means is that if we look at what we could deliver totally, if we put the load resistor down to 0, basically all the power gets burnt off in the generator, and that's the maximum amount of power we could burn. At the point where the load resistor and the generator resistor are the same, we're about half the power that's available for the system from the voltage. And that means that actually we're only delivering a quarter of what we could possibly totally deliver to the load resistance, okay? But that is the maximum that we're able to deliver, okay? Okay, and now if we look at the efficiency of power delivery versus the resistance ratio, what you can see is that actually we're only delivering 50% efficiency in the case where the load resistor is the same as the generator resistor. And as we increase the ratio, so the load resistor becomes much higher than the generator resistor, we actually end up with a much more efficient power transfer. Okay, so there are cases where we don't want to actually match and have the same impedance in both the load and in the generator. What we want to do is increase the efficiency of the power transfer, and the power amplifier is obviously a case where that is the case, where you want to have maximum efficiency in the power transfer. And in that case, we need to go over to this side of the chart. We need to increase the load resistance relative to the generator resistance, or actually in the power amplifier case, you're dealing with current sources. So the transistor, the output transistor, the power amplifier is a current source, and you want to get the generator resistance to be as high as possible and the load resistance to be as low as possible. So in that case, the ratio is actually reversed, okay? And then you operate over this side and you deliver the power much more efficiently. Okay, so we come to the next question. Why must you know your frequency? Okay, so we already know that we need to know our impedance. Generally, that impedance is 50 ohms. It doesn't have to be, but in this case, let's say we're working at 50 ohms. Okay, so now we've got 50 ohms, and we want an inductance that gives us a 50 ohm impedance. That will change with frequency. The impedance of the inductor is proportional to the frequency of operation. And so you need to know the frequency of operation in order to know what value of inductance you need. And say we were working at a gigahertz, again, this is a logarithmic scale, so it's a bit weird. But if you're working at a gigahertz around here, you need somewhere in the region of 7 nanohenries to be able to hit that 50 ohm target, okay? And that obviously goes down with an increase in frequency, and it goes up with a decrease in frequency. And the same story on the capacitor side. So to get 50 ohms with a capacitor, then we're looking at around 3 picofarads, a gigahertz or so. And again, goes, actually, the value goes down with increase in frequency and goes up with a decrease in frequency. Okay, so I've got a little example here to illustrate why you need to know what the frequency of operation is, okay? So in this example, I'm doing a little bit of matching. There's a calculator on the web. Actually, in the course, I will highlight these web calculators. Very important. If you're doing RF work, there's a lot of free stuff available on the web, and this is just one of them. So eeweb.com actually has a lot of calculators, a lot of nice stuff. And you can use that calculator to calculate the matching network you would need. In this case, we have a T matching network. We pass DC current, so we've actually got 2 inductors and a capacitor. And we're moving from a 50 ohm source to 100 ohms over on the load. So source resistance is 50 ohms. and we're using 100 ohms here. And it gives us these three values. So capacitor of about 0.3 picofarads, inductor of 4.3 nanohenries, and an inductor of 5.8 nanohenries. Okay, so what I did, I put it into Analog Devices LT Spice. Again, this is a nice free program you can download from the web, and you can run a lot of simulations and things using that. So here I've put the circuit into LT Spice, so 4.3 nanohenries, 5.8 nanohenries, and 0.3 picofarads. Okay, and we're converting from 50 ohms up to 100 ohms. So all very nice. And we run the simulation. And I should have told you, of course, because frequency is very important. It's one of the 3 questions you should know, but we were trying to work at 5.5 gigahertz. And as you can see, our peak is about 5.5 gigahertz. Okay, so here we have the phase as well. At the moment, don't worry about it. But here we have the magnitude, and we're peaking at 5 gigahertz at 3 dB down. 3 dB is basically 50%. So we've lost half the power that's being burnt off in the generator, and half the power is being delivered to the load. So we're getting a nice 3 dB peak here. And this is at 5.5 gigahertz, and we're looking basically at the 5 gigahertz ISM band. So that's the band that's used for Wi-Fi, in particular 802.11a, X, and so forth, right? So that the faster variants of Wi-Fi all use that band. So what I did next was I went out onto the Murata website, and then Murata offer a nice little calculator for simulator for their components. And if you're going to use any components, you should go to the component manufacturer. Most of them will offer this sort of calculator, and you should look at the performance of those components. And you can also download the SPICE models in the case of Murata, and that's what I did. So I downloaded a model for an inductor, 4.3 nanohenries, and another one at 5.8 nanohenries. And then we have a capacitor here at 0.3 picofarads. Okay, so we've got the circuit again. And again, running this in LT Spice, we get these results. Now you can immediately see that this is completely different. For a start, you can see that the phase where before it flowed down nicely is suddenly coming up again. And the amplitude is dropping off sharply before the 5.5 gigahertz. Okay, and if we put the two up together and compare them, you can see that at 5.5 gigahertz, here we're down 3 dB, here we're down well over 12 dB actually. So we've lost a lot of power. In fact, we're not really matching at all at the points we want to match to. Okay, so at the edge of the band, we're down 6 dB with the real components, and a little over 3 dB in the ideal case. So obviously you need to know your components, you need to know what's going on. And here again, Murata helps you. So here's the 5.8 nanohenry inductor. You can actually just take a look at the value of the inductance over frequency on the website. And as you can see, we were aiming at 5.8 nanohenries, and it is 5.8 around a gigahertz. But as you can see, it goes up, and then they stop quoting it as an inductor beyond this point. That's 3 gigahertz. Okay, and then at low frequency, you've actually got more than 5.8 nanohenries inductance. So, you know, we have a thing that's looking like that, and we're trying to work out at 5.5 gigahertz, which is actually here, and they're not quoting the inductor at those values. So what we can do is we can also look at the value of capacitor. Now, here's a large capacitor. So you say, right, I want a very low impedance, so I want a really huge capacitor, okay? And you take that large capacitor, in this case 220 microfarads, and you plug it into your circuit, okay, you should look first. Here's the impedance of the capacitor over frequency. So here's 100K and there's a megahertz, right? So you can see at low frequency, we have a capacitor, right? With a capacitor, the capacitance, the effective impedance decreases with frequency. Okay, so as the frequency goes up, our impedance is going down. And then at some point we just drop. And then we come up again and we start going up the other side. Now, a capacitor decreases with frequency, an inductor increases with frequency. So we no longer have a capacitor here. We're increasing impedance with frequency. That means we have an inductor. So on one side of this drop, and this is what's called self-resonance. So on one side of this drop, we have a capacitor, which is what we're paying for. And the other side, we have an inductor. And look at the frequency, 100 kilohertz to 1 megahertz. So that's not even what's considered RF by a lot of people, okay? So even if you're working at lower frequencies, you need to know this sort of information. You can't just go and buy a big capacitor and stuff it in your circuit and expect it to work. You need to know what its impedance looks like over frequency. And so in this case, you know, you're not going to be working with a capacitor much beyond 100 kilohertz, okay? Its impedance is very low. So if you just need a very low impedance, I mean, we've got 1 ohm here, even as we're getting up to a gigahertz, right? Then it will still look like a low impedance, but it's not capacitor at these frequencies, it's an inductor. So the final one, what is ground? And where is my ground is an important question that you should ask. Okay, so we have lots of grounding issues actually. Grounding issues come up a lot. A lot of problems are caused by grounding issues. There is truly only one true ground, okay? And the true ground would be somewhere in the center of the earth, right? That would be where the true ground is, okay? Now, where your ground is not necessarily where the true ground is. And unfortunately, we've started to use this term ground for all sorts of different things. Okay, so you go back to, I think it was 1839 in the telegraph, and what did Samuel Morse do? So he put in a single wire. Okay, single wire is good, saves you money, right? You don't have to trace 2 wires across the country. And this being electricity, you actually need a return path, right? And that return path he did by putting a ground in. So he actually put either a large copper stake or a large copper chunk of metal in the ground. And then at the other side, he did the same. Now, what that means is that the current will flow along the wire that you strung up across the country and then flow back through the ground. Remember, you must have a return path. And that's what the ground is doing in this case. A lot of people forget that the ground is acting as a return path. So there is current flowing along this ground through the earth effectively, okay? And you need to remember that. So that's the 1830s, 1840s or so, okay? And we come to the situation today, and what do? So we draw our schematics and they give us a ground symbol. So we stick ground symbols everywhere, right? So you stick them at the bottom of the transistors and you stick them on your supply, and it's all hunky-dory, except you've got to remember that there's no such thing as a ground, okay? There's going to be one point in this circuit, and in this case, it may well be here, but it may not be. You've got to remember that, where the current will flow back to. And if we look at this circuit, we could maybe break it down in this way, where we've got inductors in both the power supply and the ground return, okay? And so these inductors will have impedance associated with them. I mean, in real life, they'll also have some resistance. And current flowing along these inductors will experience an impedance drop. So there will be impedance drops all around your circuit, okay? And you need to be aware of them. You need to know where your grounds are, where your current should be returning to. Another point is, you know, if we drew all our circuits like this, we wouldn't need any decoupling capacitors on the supplies. Okay, well, we actually need decoupling capacitors. And where you return your decoupling capacitor to is important. In this case, this could be, say, a power amplifier. And it turns out that you need to return the current from this supply on your driver stage to the ground on the output stage, because there's a loop round the transistor that needs to be completed. And if you go round the whole thing, then you start losing efficiency. So ideal current return, it's not necessarily on the generator side. Okay, so generally think of a DC supply with some sort of circuitry, a load, and then we return to the DC supply. And that's definitely true for the DC, right? The DC is definitely going from and back to, say, the battery or the DC supply. But in the case of a transistor, we could be generating the frequency locally, or we could be taking an input frequency and then generating an output frequency. And in that case, you want to return the current to that transistor. Now, it may not always be possible to do it as straight as this. I mean, if you're going off chip, for instance, this would be, say, a bond wire, and you would have to come back through that bond wire to that transistor. But you need to return the current to that transistor and not to the DC supply up here that's driving the whole thing. So you need to know where your ground is in this case, and we're using the term ground very loosely, and we shouldn't be, but that's the case, right? So in this case, the ground on this load is not to that ground, it's actually here at your transistor. And so you need to get that current back to that transistor and not down to this ground here. Okay. And we can have a bad return path, as I said. You want to get the return path from this load, because it's being driven by this capacitor, back to this transistor. Sorry, driven by this transistor. You want to get the current back to this transistor. But you neglect to do that, and you use another path which goes through to this transistor and then has to come all the way around through here before being returned to here. Now, the problem with that is therefore that all of this becomes part of the ground that this transistor sees, and anything happening with this transistor can crosstalk into here. You can have all sorts of issues. The gain of this transistor can go down because of that loop and so forth. So you need to understand where your return path is. And in this case, you know, we need to connect here, and maybe we need to actually cut this line here. So we need to connect here and cut this line here. And then we actually need to consider the current flow. So if we're using microstrip, which is one of the ways that we move signals around on PCBs, we're using microstrip, the signal goes out one way and then actually comes back underneath in the ground return path. Okay, so we put signal out one way, we get the ground return path. So where's the return path in this case? We have two grounds, and this is very common. You've got grounds you don't want to mix. So we've got two grounds, but we have signals crossing both. How's the current going to get back here? The answer is going to find whatever route it can, and that may well be actually through the power supply itself. So it may have to go off board and back on board to be able to do that path. And in some cases, you could even have an antenna. So you've got a signal crossing two two ground supplies, two ground planes, and you end up with an antenna, and that radiates power out. So not only do you lose power because you're radiating it out, but it can also be picked up by another antenna potential somewhere else. Could be completely the other side of the board, and you're left debugging really weird problems because one side of the board is talking to the other side of the board. So you say, well, okay, let's join the two sides. So let's put a little join in there, just a small one, so that we don't have too much crosstalk between the grounds. So in this case, we got the signal coming across, and then the ground's coming back. But here, it's got nowhere to go. So what's it do? It has to head off round until it finds our little ground bridge, crosses, and then comes all the way back here. Now, all sorts of things can happen in the meantime. I mean, quite apart from the fact that you're probably increasing the impedance in the ground, there could be other signals coming across where it could mix. So again, you can get crosstalk between signals actually on your ground because it's doing this. So what's the solution? We put a ground bridge in, but we put the signals across that ground bridge. So whenever you put the ground bridge in, you put the signal that's using that ground bridge across the top of it. And in this case, the signal, the ground will flow through that bridge there. And say this signal started off over here, came down, and had to go off over here. You still wouldn't cross here, which would be the shortest route. You would have to go back to that ground bridge and then come back again, okay? Now, we obviously are putting signals close to each other and they can talk to each other. So it's not a be-all ground solve problem from that point of view. You will have to check that these aren't coupling to each other. If they are, you may have to have another ground bridge at some point. There can be all sorts of issues involved, but this is the way that you move signals between ground planes on a PCB, okay? So always make sure that there is a solid ground plane underneath all your signals, and that goes even at mixed signal level, down at a few megahertz. You need to be doing this sort of thing when you're moving signals around. And if you're going across ground planes, then put in a ground bridge, make sure that the signal is flowing, is over that ground bridge so that the return path can flow through that ground bridge. So here are your three questions again. What's the impedance of the system I'm working in? What frequency am I working at? And where is the ground? Okay, so we'll cover a lot more in the online course. Again, being organized through Wizlogix. 5 days, 1.5 hours, total of 7.5 hours of classes. And hopefully by the end of it, you'll understand RF fundamentals, be able to work with transmission lines and so forth. You'll understand the performance of passive and active devices, and you'll be able to track down grounding and signal return issues and find online calculators. Very important, lots of online stuff available. I'll give you pointers to it. That ends the webinar. Thanks a lot for listening, and I'll hand it back to Leona, who's our host for today.
We have come to the end of our webinar today. Thank you, Malcolm, for your informative sharing. Goodbye, everyone. Thank you.